Today, let's talk about how to size a rocket. There are a lot of tools available to figure out what size of a rocket you need, but today I thought that I would go through some of the basics of how to actually make this type of a decision. So what do we need to figure out for sizing a rocket? Well, the first thing that we need to figure out is the size of what's called the payload mass. And the payload mass is like the satellite. We need to figure out how much fuel we need to actually get into orbit. And then obviously, you need some sort of a container to actually hold all that fuel, and you need engines to use that fuel. And so the last two things are actually quite difficult to figure out. So we're going to talk a little bit about all of these different steps today and how to do this simplistically. It is super, super complicated. So we're going to gloss over a lot of the details here, but we're just going to give you sort of a flavor of how you would actually do this. All right, what are the steps that we actually go through? Well, the first is we start with the payload size and the desired orbit. Then we get an initial estimate of the amount of fuel that we would take. And then we're going to calculate the size of the infrastructure that we need based on the initial estimate of the fuel. So how large of storage tanks do we need and stuff. And then we're going to calculate the final mass given the amount of infrastructure that we're going to need. And then we're going to figure out how large of the engines we need, or how many engines we actually need to get us off the ground. So the first one is the payload mass. So that's basically how big the satellite is going to be. And satellites come in all sorts of shapes and sizes. The smallest satellites are, about the size of a softball, 4 inches by 4 inches, or 10 centimeters by 10 centimeters by 10 centimeters. Those are called CubeSats. Those are sort of the smallest possible satellites that we put into orbit, and those are often let go from the International Space Station. And then we have satellites which are much, much, much bigger, and those satellites do a lot more. And those things can be 10,000 kilograms or larger. So they're massive. They're about the size of a bus. Those are sort of normal weather satellites or communication satellites. Okay, so we're going to use that 10,000 kilograms as the size of our satellite, because that's sort of a normal size of a satellite. Now what we're going to do is we're going to estimate the amount of fuel that we need. And we can figure out the amount of fuel we need by using the rocket equation. Once again, we use the rocket equation. And the rocket equation, if you remember, is this mass of the rocket plus the fuel is equal to the mass of the rocket times exp of the delta V divided by the exhaust velocity. The exhaust velocity is really, really, really important here. Hydrogen and oxygen gives a really good exhaust velocity, but it's very hard to store, and it makes the rocket actually really complicated. So we're going to pass that by. We're going to say NASA can deal with hydrogen and oxygen, but we're going to use something a little bit easier to handle. And we're going to use RP1, which is rocket propulsion 1. So we're going to put RP1 plus oxygen. It gives a worse performance, but it's much easier to store, and it's much less complicated. So now we need to calculate the delta V that we need. We need to figure out where we want to actually go in our orbit. So the delta V is the amount of velocity we need to actually get to orbit. And we need actually 2 velocities. The first velocity that we need is around the Earth. So that is the velocity of a low Earth orbit satellite. And then we need to actually go from the ground up to that altitude. And so we need a vertical component of the velocity, and we need a horizontal component of the velocity. The horizontal component, like I said, is the orbital velocity, which is roughly 7,650 meters per second. If we're at like 400, 500 kilometers altitude, which is where a lot of satellites are. So the orbital velocity, roughly 7,600 meters per second. The vertical velocity is basically how to go from the ground up to about 400 kilometers, right? And you need about 2,700 meters per second to get up to that altitude. And so we need to combine these two, but we don't just add them. We add them as a vector, and so we add their squares and we take the square root. And that means that we have roughly 8,100 meters per second to get to orbit. If we want to get to an orbit at 400 kilometers altitude, we need roughly 8,100 meters per second. So let's take those numbers and let's get an initial estimate of the amount of fuel. And so we're going to use the rocket equation, like I said, where the wet mass, the total mass of the rocket, is equal to the dry mass, which is, for us, the mass of the payload, times exp of delta V over exhaust velocity. The mass of the payload is about 10,000. The delta V needed is 8,100. The exhaust velocity is about 3,000. So we have all the numbers in all the right places. So you take 8,100 divided by 3,000, you get 2.7. You take the exp of 2.7 and you get 15. Then you multiply 15 times 10,000 and you get 1,500 kilograms, all right? That is the mass of the fuel plus the mass of the payload. So if we subtract off the mass of the payload, then we need 140,000 kilograms of fuel to get our 10,000 kilograms into orbit. That's a lot of fuel. 140,000 kilograms to get our 10,000 kilogram satellite into orbit. It's a lot. But this is a simplification of things, right? And so far, we haven't actually even talked about the rocket yet. So what we have right now is we have the satellite and we have just a big pile of fuel. We have no container or anything at all. And so we need to estimate how much infrastructure we need, like storage tanks and stuff, to actually store this fuel. For the infrastructure, we need storage tanks, one for the fuel, one for the oxidizer. We need engines. We need some sort of an outer casing to hold it all together. We need a lot of pumps and stuff like that. We're going to simplify all of that stuff. It's really hard to calculate all of this stuff. We're going to sweep all of this under the rug, and we're just going to make an assumption. We're just going to say that it's 1/10 of the mass of the fuel. So the fuel is 140,000 kilograms. So we'll just say the rocket itself is 14,000 kilograms. Very, very approximate. So now let's calculate how much fuel we actually need, because now we don't just have our payload, but we have our rocket too. So we have rocket mass plus the payload mass as our dry mass. So we use the exact same equation, but instead of using just the payload mass, we're using the rocket mass plus the payload mass. So when we do that, we have the 10,000 plus the 14,000. We still multiply it by the exp of this 8,100 divided by 3,000. Which is the exp of 2.7, which is the same 15. But now we have to multiply that by 24,000 because that's the mass of the rocket plus the payload. When we do that, we end up with 360,000 kilograms. That's how much fuel we actually need. And we're assuming that our rocket that we created can hold all of that fuel. So the amount of fuel that we need is this 360,000 kilograms minus the mass of the payload, which is 10,000, minus the mass of the rocket. So the fuel that we need is 336,000 kilograms of fuel to actually get to orbit, taking into account the mass of the rocket and the mass of the payload. Once again, lots of assumptions here, but it's sort of a rough estimate. Now what we need to do is we need to size the engines, right? How many engines do we actually need to do this, to get us off the ground? To get us off the ground, thrust has to be larger than gravity, right? We're sitting on the ground, we're thrusting up, gravity's pulling down. If gravity is larger than thrust, that means we're just going to sit there or we're going to fall, right? But if thrust is greater than gravity, then we'll start lifting off. And so thrust has to be larger than gravity. So we write down the thrust equation, which is mass flow rate times exhaust velocity, and that has to be greater than the mass times the gravitational constant of the Earth. If you move the exhaust velocity over to the other side, because we know what the exhaust velocity is, it's around 3,000, we say the mass flow rate has to be larger than the mass times gravity divided by the exhaust velocity. You put in all of that stuff. You have 360,000 kilograms for the mass of the rocket, times 9.8, which is gravity, divided by 3,000 meters per second. And then you do that, all that math, and you come up with the mass flow rate has to be larger than 1,176 kilograms per second. If the mass flow rate is exactly that amount, the rocket will just sit there. If you make it larger than that, the rocket will start taking off. If you make it much, much larger than that, the rocket will just go into space very quickly. A SpaceX Merlin engine uses around 310 kilograms per second of fuel and oxidizer. So we would need 4 of those engines, and that would allow you to just sort of rise slowly off of the launch pad. So then if you wanted to calculate how long it would take to actually do this, we have 336,000 kilograms of fuel. We have a mass flow rate, which is 1,176 kilograms per second. You divide those two numbers, and this is going to take roughly 286 seconds, about 5 minutes, to run out of fuel. Okay, so in summary, we have just made a rocket. And NASA makes some tools available for doing this for us. So we don't have to go through this math every time we want to go to orbit. We can just go to this tool and we can plug in some things and it will tell us what rockets actually to use. But if we don't use this, then we can roughly calculate the size of a rocket using the rocket equation. We need to guess at several things here. The exhaust velocity is the first thing. And then we need to guess at the mass of the storage tanks and engines and all of that stuff. When we estimated that as 1/10 of the initial guess of the fuel, that is totally a guess. And it just allows us to estimate the size of the rocket. This totally neglects stages, which would reduce the amount of fuel that we need also, but it makes our calculations quite complicated. So we just totally ignored stages. So this is very approximate, but it gives us a rough idea of how much mass it takes to actually get to orbit. To get 10,000 kilograms to orbit takes a rocket that's roughly 350,000 kilograms in size, using all of these rough approximations.